Thanks very much. So the final talk before the group discussion will be given by Travis Humble from Oak Ridge National Laboratory, High Performance Computing with Quantum Processing Units, Systems and Software Concerns.
Thank you for the introduction, Jonathan, and Irfan, thank you very much for the opportunity to come out and speak. This is actually my first time visiting Berkeley, the university, and Berkeley, the laboratory. I got to see the Golden Gate Bridge today, and probably a little bit cooler, I got to see Alcatraz. So thanks for clearing up the weather, too. I appreciate that. So yeah, the title of my talk is High Performance Computing with Quantum Processing Units, and there's a little bit of a cleverness in the title here, System and Software Concerns. And I use concerns here both as a topic of conversation and maybe something to kind of fret about. So the point of the conversation, though, is to try to talk from a high-level perspective about how the devices that a lot of the talks today have focused on can actually be used. And for me, I'm kind of this top-down thinker type person, and I really need some kind of understanding of why we're pursuing this area. And of course, it's the future of computing that we're talking about. And from that perspective, there are demands that our users have, either in security or commerce or scientific discovery, for new computational power. And in the past, we've always achieved that using these CMOS-based technologies, coming up with new device designs, slightly smaller features, maybe even improving our programming. But that seems to be coming to some kind of end. At the same time, there's also all these remarkable features that quantum information theory suggests that we'll be able to do. And we've seen some great talks about demonstrations of that. So at the bottom line of this is, what are the demands that quantum computing is going to satisfy? And of course, being at a Department of Energy facility, the thing that I focus on are the scientific applications. And I think there's sort of two groups here. One is what's been called quantum simulations. I do a lot of numerical simulations, and that word simulations always messes me up. So when you tell me you're doing quantum simulations, I always have to ask, do you mean experimental or numerical? But we've seen talks today focusing on chemistry, materials science. There's even high-energy physics applications we can consider. But there's a second group of applications that I would put more in the applied math arena, things like linear algebra and optimization. And I think this is a really important area as well, because we see things like data mining and artificial intelligence emerging as key applications for the future, and quantum computing may intersect there as well. Now, the progress that we've seen in quantum processing units is, I think, what drives a lot of the discussion today. It's certainly what drives me and my research in considering how we would use these ideas from quantum computing for scientific applications. And so programmable QPUs, it's kind of an analogy to CPUs or GPUs, of course have been realized. And the ability there to do these demonstration algorithms, whether that's things like factoring or search or chemistry or optimization or whatever it will be, kind of sets the tone for where the future research will go at the device level. So there seems to be a lot of focus right now on understanding the engineering concepts, some of the infrastructure integration that Robin had just mentioned, and then the low-level instruction control. But this isn't the level at which I want to talk about. I kind of consider this the device level when it comes to high-performance computing. What I want to do is try to set a framework in which we can compare these types of devices to the state-of-the-art scientific computing facilities that are hosted in places like the national laboratories. And when it comes to scientific computing with conventional processing, massively parallel systems are the state-of-the-art. And the idea there is that there are some scientific problems that are so complex, their scale is so large, that theoretical, analytical efforts to solve those problems are probably going to fail. I need to turn to something that's a little bit more automated, a little bit more machine-based. I need to be able to manage the complexity of those systems. I need to be able to represent the information those systems provide using these massively parallel systems, in part because they provide a lot of processing power and they provide a lot of storage power. Now you can see here there's a list of the top 5 supercomputing systems in the world right now, at least as of November. 2 Chinese systems, Taiyu Light and Tianhe 2 top. the list, but I'll just call out Corey down at the bottom, which is a nurse machine located here at Berkeley, as being in the top 1% of this listing. The thing you'll notice is that they're all under 100 petaflops, okay, so floating point operations per second. But by the early 20s, we're expecting there to be exaflop systems available. Now, the reason I wanted to highlight this is because that's the bar at which we need to compare these quantum processing units and their impact on scientific computing. And maybe by the early 20s, they're ready to provide that impact, or maybe it's a few years later. But when it comes time to make that evaluation, these are the types of systems they'll be compared against. Now, in modern high-performance computing, an accelerator architecture is one of the more dominant paradigms. The idea here is that I have a network of processing nodes. Those nodes consist of different devices. CPU, of course, is present as sort of the driving force behind the node. But there can be other devices as well, what are known as accelerators. GPUs are very popular in this regard right now. They may be integrated tightly into the device. They may be loosely integrated, hanging off through some kind of bus. Quantum processing units may be suitable as an accelerator in HPC architectures. And I say may because there's a series of questions that I think raise a concern about whether or not that's actually true. So first off, what is the overhead to switch between computational models? So the HPC systems are built around this CMOS-based technology, a very von Neumann approach to computing with a very specific programming model and execution model. And yet, quantum computing takes a lot of way from that conversation, but it also is inventing new ideas and concepts. So how do we switch back and forth between those two models efficiently in order to carry out scientific computation? Short ones. I'll give you an example in a second. Yep. And there's other concerns as well. So example, what is the functionality about the processor that needs to be exposed? How does it actually behave? Okay, what are the constraints that it places on the user? And then finally, how do we benchmark that system and make that comparison, for example, to the top 500 list? Now, an alternative to this model is that I actually just develop special purpose standalone devices. And these actually have a lot of value. And I would say that some of the experimental demonstrations that we've talked about fit this model. That you make a highly sophisticated and specialized implementation of quantum computing that maybe can't be reused. Maybe it gets put on the shelf when it's done, but it still serves its purpose. I think this is a completely valid way to solve that, but that's not the approach I want to consider. So I want to motivate first the idea of the system and software concerns by postulating a component model for what one of these nodes looks like. Again, you can see up here, this block diagram just shows that there's different parts to what a node is. There's the CPU, there's the QPU. I want to break up the QPU now into three specific parts: a control unit, which is responsible for expressing an instruction set architecture that the device implements. It outputs opcodes, the things that are interpreted by the execution unit. That is the part of the device that actually performs gate operations, but it performs those gate operations by outputting fields. Those fields are essentially triggered by whatever the opcodes are. Those fields then apply to a register, and the register is where the qubit lives. This is a very high-level model, but I think it can fit all of the types of different quantum technology devices that are out there if you draw these boxes big enough. So, of course, developing this type of model for how nodes behave exposes the interfaces between their different parts. It also specifies now that there are different languages for talking between those different parts. So at the very high level, there needs to be a programming language. But below that, we actually have to have an executable. So when we go to run this program, there is some, in a conventional sense, a binary that is being executed on an operating system that is issuing these instructions to the QPU, which serves as a device. And so developing that type of system is something that I'm focusing on. That device itself now exposes this instruction set architecture. That instruction set may be something as simple as, Clifford plus T. It may be something that's more complex. There may be very complex instructions. You can think of the D-Wave quantum annealing device as exposing an annealing instruction. But there's a very specific set that you essentially have to translate that program down to. The FTQEC operands or opcodes are is the place where I'm going to put fault tolerance. Now, this is probably the most debatable point about this model, is that easily you could put fault tolerance a little bit higher up in the stack of these languages, but for sake of argument, we're just going to place it down where the execution unit is. And then, of course, there's actually the gate fields themselves. So how do I describe the arbitrary waveforms that need to be generated to apply to these different physical systems? Now, in terms of the execution model for how this node behaves, you can see here are the different pieces of that node, the CPU on the left and all the way on the right, the register. This is a sequence diagram. You read these from the top to the bottom. The arrows moving back and forth denote the transfer of information between these different components. So, of course, my CPU issues those instructions, and we follow through this listing of 10 easy steps in order to generate a return value. Now, the place where quantum mechanics happens is over here where the fields are actually applied to the register. And when I say collect fields, you can think of that as being readout, okay, so detection. But everything else in this execution stack actually represents classical processing. But it has a dependency on whatever those fields are that need to be applied and whatever data is collected in that step from the register. So now I'd like to give you an example of this type of software and system stack using this D-Wave 2X processor. And the reason that I use this is that it has a very well-defined interface and specification, so it allows us to go through a complete example. So for this crowd, it's probably overkill to give an explanation of what the processor is, but in case there's anyone who doesn't know, it is a superconducting integrated circuit. Has a certain degree of programmability to it. It can hold up to 1,000 plus qubits. They're in a very specific connectivity arrangement. It's called chimera. But it is a special purpose device in the sense that it solves an optimization problem through this principle of quantum annealing. So you input some data, you execute the problem, and then you read out some data. And that's essentially the process. Now, it performs it in a very specific way, using a very specific annealing schedule. You can see here with the red and the dashed blue lines. But for our purposes, this is enough detail to describe the execution model. Now, in terms of the programming model, we understand that there is a sequence of steps that are needed to take classical input data, map it onto the hardware, and then read it back out. And this is going to get to the question you're asking, Joe. For the D-Wave processor, there's I don't think it's unique to this system, but there's sort of an interesting point where the data that is provided to the processor is first represented in the form of a graph. And that graph information actually has to be represented now into the hardware connectivity. And this process of mapping one graph into another is actually known as minor embedding. It's a NP complete problem in general. Now, there are good heuristics. So if you know exactly the structure of your graph a priori, you can come up with some rule sets for performing that mapping. But in general, it's very hard to do. And then, of course, there are additional steps that you have to perform. Now, when we add the program and the execution models together, some of this is derived from the open literature about D-Wave. You can see starting up here at that top right red box that says Kubo formation. I think I skipped over explaining that Kubo is a particular quadratic unconstrained binary optimization problem statement. That's the input data. And then this sort of series of processes in red correspond to sort of a classical computing stage. The processes in green correspond to a stage responsible with setting up the firmware state of the hardware. The blue is where we actually perform quantum computing, and then there's some post-processing stages as well. So we wanted to look at this whole system from a systems perspective for the purposes of modeling how it performs. Of course, we can run these programs on the D-Wave. For example, NASA can provide access to this, and we can do timing statements, and we can collect statistics. But we wanted to make a model for how the system itself behaves. For that, we use in the conventional computing community what's known as a hardware modeling language. ASPEN is something that was developed at Oak Ridge by our Futures Technologies group. It essentially allows us to provide, just using regular text files, some statements about how we expect the hardware to behave, how we expect the program to behave, and their dependencies on each other. And I won't go too much into detail, but the software itself is available at the website below. The way that we're going to use this is we're going to make statements about what the machine model is, and we're going to make some statements about what the programming model is. We're going to put it through the ASPEN simulator, which essentially counts up the resources that are consumed, and then from that makes estimates of how it performs. So as the first stage, you can see here we have a statement about the hardware model for the both the D-Wave processor, which is going to be characterized in terms of the amount of time it takes to perform an anneal and the number of sampling steps that it takes. We also have an Intel, I believe, an Intel Xeon processor, which we use to characterize the classical computing stages. In the pre-processing stage, we're going to use some estimates for the complexity of an embedding algorithm. This is actually what known as the Chi-McGreedy-Roy algorithm. It's what we believe is implemented by D-Wave in their device. We have our own implementations of it. There is an average case complexity. It ends up depending on the structure of the input graph as well as the structure of the hardware graph. And so this gets encoded into the programming model. This is stage 1. Stage 2 is the execution. Again, this includes things like setting up the paramagnetic memory in the hardware and thermalizing the results, initializing the register, and then performing the annealing. And then finally, there's a post-processing stage. And this really just corresponds to sorting the different energies that come out of that sequence. And then we put all of this into this ASPEN modeling framework in order to get out what was the time to solution. And so here are the timing results that we observed, and it's basically what we expected. Stage 1, you'll see as a function of size, and this is the input size. The solid red line represents the amount of time that the ASPEN model predicts is required to embed classical data into the hardware. And you can see it grows rather quickly, and that's exactly what we expected based on the complexity statements. The dashed red line is actually our experimental results, and they don't agree. They're within a factor of 2 of each other, but their slopes don't exactly match. Again, we're using average case complexity, whereas the dashed red line is actually an average over 1,000 instances at each point. So it's probably within the error bars, but we don't have error bars on here. And then the green line is just the amount of hardware that we needed to consume in order to perform those embeddings. You'll notice that the y-axis there is time in seconds. We're almost always taking more than a tenth of this. Oh, yeah. Oh, yeah. In the very beginning. Yeah, I apologize. Exactly right. Yeah, so I have some, I apologize for that. I have some doubts about the accuracy of those very small size simulations, because that's actually saying how long does it take to embed one node. So yeah, that's the issue that's going on there. Thanks for catching that. But you'll notice that the time over there, it's on a log scale. It's nominally in seconds. If I look at stage 2 and stage 3, I can see that for stage 2, which is the part that actually does quantum processing, is on the order of microseconds, hundreds of microseconds, but microseconds. And the only reason that it goes up at all is because I have to assume a certain amount of error in every time I run this, so I have to perform a number of samples to reach a desired accuracy. I think our threshold was 99%. So there's actually a slight increase in time, but each run is only 10 microseconds, so it's not very big. And then stage 3, this is actually on the order of microseconds itself, just to do this bubble sort algorithm, okay? So if I look at these 3 stages, the piece that actually dominates my system is the first one, which is the classical processing problem of translating input data into the processor. And so this is a place where the computational overhead pops up. In order to go from what might be a convenient representation classically as a kubo into the icing model on a very resource-limited connectivity, I actually hit a wall. And this was actually referenced earlier this morning in your remarks, Willis. So these results certainly are. The reason I think that it may have a further-reaching implications is that even in gate-based models, there's a certain dependency graph that pops up, which says at this execution time, what qubits have to be interacting with each other and which ones cannot be interacting with their neighbors because they have commitments to other interactions. And so that constraint satisfaction problem is another one that shows up. And that's in a gate-based approach. That's the kind of thing that you can try to solve ahead of time. It's the kind of thing that a compiler would normally do. But if you have any feedback-driven circuit behavior, so for example, syndrome measurements, then you may have to on-the-fly recompile your circuits in order to satisfy those dependency graphs. And that's another place where a bottleneck might show up. I don't know for sure what the timing will be there, but that's a concern. So the ASPEN modeling language is very convenient. It's very easy to use, but it's not quite the level of detail that we're interested in. There is another tool known as the Structural Simulation Toolkit, very popular within the computer modeling community. It is essentially a discrete event simulator, and you define components within this model, things like CPU and QPU, and then you define event handlers for those components. So when an event is triggered, so for example, I tell the QPU to initiate an instruction, that event handler is passed off to the discrete event simulator, which then will account for what should happen next in the execution model. And from that, you can collect statistics about how much time is spent at the QPU waiting for the instructions to complete or waiting to fetch instructions from memory, these types of considerations. And so we're now moving away from the ASPEN modeling into this more detailed, fine-grained simulation. And to give you an example of where we are at the moment, this is an abstract machine model of what a single node would look like in the case where it had CPUs, QPUs, memory controllers, and a different hierarchy of memory cache. Just zooming in on this region for a second, this block diagram points out that there is the QPU controller right here, which is responsible for fetching instructions from the QPU bus. That's connected outside of this frame to the memory controller. And then over here, it's labeled QPU processor, but this is where the execution unit itself resides. And so that's the type of model that we're moving to next in order to do these types of simulations. The node model that we get from that, though, isn't quite the whole story. Because, again, as I pointed out, in this accelerator approach to designing HPC, I may imagine that these accelerators all have access to a QPU. And so you can see here that there's at least 3 different designs that we can think of. The first one, this asymmetric model, actually has an HPC system connected to a quantum computing system directly. Okay, so it's kind of a standalone. There may be some client-server type interaction. It makes requests. It gets back information. The middle one is more of a traditional accelerator model. The nodes here all have QPUs. They're able to talk to each other via an interconnect. This is exactly how, say, Titan, the HPC system at Oak Ridge behaves. But I think that this particular design has a problem with it, which is that, of course, the QPUs, the quantum processing units, their registers are now isolated from each other. And, you know, this is the simplest math, right? But, of course, the dimensionality of the Hilbert space grows as the number of qubits. But if those qubits can't talk to each other, then we actually get an exponential reduction in the size of the Hilbert space. Now, in order to recover that, of course, we need some kind of quantum interconnect, like we see down here. And so you can see that there's a certain symmetry in this quantum accelerator model where the classical internet and the quantum interconnect both serve the nodes, but they do them in different ways. Now, of course, there is a penalty by having a quantum interconnect, which is now we have to synchronize operations across the nodes. We get this quadratic increase in the amount of communication that's required, assuming that every node has to talk to every other node. In fact, the exact communication pattern is going to depend on what's the algorithm that we're trying to execute. So in the first, actually, I'll go to the next slide. So yeah, so here's an example, and Jared, I know you know this figure because I stole it from one of your publications. You can see that in this variational approach, that middle accelerator model without a quantum interconnect actually is perfectly suitable for this algorithm. All right, so you could imagine partitioning up the calculations of the different parts of these Hamiltonians to individual QPUs, and then doing a what's kind of called a gather operation in order to collect all that data back together. But if you wanted to move something that either had required a register size that wasn't available on an individual QPU, if you moved to something where you had to decompose your problem up across individual QPUs, then not having an interconnect available would actually be a very big issue. So we're looking at that. We're looking at trying to understand how the quantum interconnect itself should work. And to that end, we've developed a quantum networking environment, something based on the idea of a interconnect, or really a switch that allows nodes to talk to each other. They have both quantum and classical network interfaces. There is a controller. This is software-defined networking for those of you who've heard of this before, that is responsible for setting the protocol for communication between those different nodes. We don't yet have a quantum switch that can perform the way that we want it to, so instead we're using numerical simulation as the back end for this type of model. So the software available at the website down here, in fact, we just got it up this week, so if anybody wanted to be our guinea pig for testing this. The software there will run the same in the actual system, the actual testbed system we're developing, as it would with the simulator. The main difference being that the simulator has to implement a very particular method for modeling the transmission through the different channels. And to give you just a very specific example, we've done this using superdense coding, which is a protocol for using entangled states for transmitting classical information between nodes. We added a layer of complexity to this by adding forward error correction to the transmission. And so it becomes necessary for the nodes on the classical network to negotiate with each other which error correction to use. And they do that depending on what error rate they're observing. And so in the plots that you see here, this is actually for a depolarizing noise model. There is a probability P of error, and then there's a bit error rate on the y-axis. And this just shows you what that bit error rate is for different classical error correction codes. But the point is that this network simulating environment allows us to negotiate that at the classical level and then implement it at the quantum level. We want to take those abstract machine models we're developing for the nodes and port that over into this so we can make a full interconnected system description. So getting to the very end quickly, at the moment we are focused on these ideas of time simulations of single QPU-based algorithms, and then moving towards time simulations of these inter-QPU communication protocols. We think that the execution and programming design choices that are made here are going to have a big impact on the performance, because a lot of what I didn't talk about was that the device characteristics actually fuel a lot of the parameters that determine these models. But in the long term, we need to understand better the instruction set architectures and the opcodes, figure out a good way to model that without having to go to large-scale quantum simulations, and then also address what is the memory and power usage. So one of the things that we've looked at recently is how much energy does it take to flip a spin, say, in a semiconductor or superconducting technology? And it's almost nothing, right? But how much energy does it take to generate the energy that you use to perform that gate operation is actually a separate question. And as the technology itself matures and becomes more integrated, becomes, I want to say commercially viable, but that may be too strong, but we'll just say mature, making estimates about how much power that is going to be consumed may have a big impact on whether or not people can afford it. And then finally, in the very long term, we think that these types of tool sets can be used for identifying performance metrics and best practices for algorithms and programming choices. And so with that, I'll throw up a summary of what I think are the main points. I won't list it through it. Instead, I'll just thank you for your time and a wonderful conference.
We have a time for a couple of questions for Travis.
Yeah. No, I think I understand your question. So what does FTQC opcodes mean? And I did not give you a great explanation during the talk. But of course, if a quantum processing unit were to implement fault tolerance error correction protocols, my opinion is that is at the device level. Okay, so the programmer, the user, the system actually should be kind of agnostic to that. So when I ask for a C0 operation from my device, I send it an instruction for C0. The device then has the responsibility of translating C0 into whatever's the fault tolerant implementation of that. And so when I say FTQC opcodes, I just mean that part. Exactly right. Yeah. And then that is a choice. I think there are alternatives to that, but I'm kind of going with that one first.
Cool.
Yeah. Nope. Yep, exactly. So I think in some ways that question for me also gets at what about the physical infrastructure that is required, and that is very technology specific. But I certainly think that there is some great work within the trapped ion community using, this is from Duke and UMD, on using optical interconnects for performing entanglement swapping operations between trapped ion devices. So that's an example of how I can see that behaving. For other technologies, I'm not quite as sure. In the back. So that's a great question too. The truthful answer is I don't really know, but I'd give you a best guess. I think that at some level, some type of optical interconnect may actually end up being very advantageous because the cooling capacity for these type of dilution refrigerators is limited. And if all we're pumping into those are our electrical signals, I think we'll eventually reach a point where the cooling capacity is kind of met. On the other hand, optical signals don't generate quite as much heat. And so that may actually be a viable way of stuffing more qubits into the refrigerator to begin with. It's speculative, but that's an alternative.
Okay, I think we better close there and thank the two speakers this afternoon.